Let's turn that dial up a notch and talk about another graphing problem. This one a little bit tougher than the previous ones. So here I have this equation, y equals 8 over x squared minus 4, and it looks right now like I've got a pretty simple fraction just like before, but remember you can factor this into 8 over x minus 2 times x plus 2. So that's really important to factor our denominator because now I have two vertical asymptotes. If I set my entire denominator equal to 0, what you're going to find is I have two possible values for x that will make this thing equal 0. So that means I'm going to have a vertical asymptote of x equals 2 from this factor, and I'll have a vertical asymptote of x equals negative 2 from this factor. So let's put those two vertical asymptotes down. I've got x equals negative 2, and I have x equals positive 2. All right, next up, the y-intercept. The process is exactly the same as the last one. So let's set the x equal to 0 and solve for y. 8 over 0 minus 4 is going to be 8 over negative 4, which is going to equal negative 2. So that means I've got a y-intercept at 0, comma, negative 2. So let's plot that on our graph. 0, negative 2 is right here. And let's even label that. So that's going to be 0, negative 2. All right, next up, let's talk x-intercepts, and I want to set the y equal to 0. And if we take a look at this, this is just like the examples we saw before. I've got a numerator with no x's in it, and it's just one fraction. This will never equal 0, so this is a none scenario. No x-intercepts will ever equal 0. All right, now let's talk about the end behaviors. If I take my limit as x approaches positive infinity, let's think about what happens. As I put in really large numbers, this thing explodes, and I'm going to subtract 4 from that, and so this is going to be getting closer and closer and closer to 0. So that's going to be the same thing with my limit as I go to negative infinity. 8 divided by a really large number is going to equal 0. So what that means is that my horizontal asymptote is going to be at 0. All right, and now we're ready to talk about graphing this thing. Let me write down the horizontal asymptote. And at this point, it's looking like if I have, really I've got these three sections. Something's going to happen when x is less than negative 2. Something's going to happen when my x values are between negative 2 and 2. And then something else is going to happen when my x values are greater than 2, or I could say 2 is less than x. And really, if I kind of either plug in some points to figure out where my graph is, or I can kind of use some mental math to think about where this graph will be, that's going to be how I'm going to actually put down my curves. And if I think about taking a number that is less than negative 2, that means that when I square it, it's going to be a positive. I'm going to subtract a value. So if I have a number, let's say negative 3, if I square negative 3, I get 9. I subtract 4. This fraction stays positive. So for all values where x is less than 2, my graph is actually going to be positive in the y values. So this is where this first section comes from. When x is between negative 2 and 2, when I square that x, it's going to be a number that is less than 4, which means that this denominator will be negative, which means that all of my y values will be negative, which should make sense since I already have a y-intercept down here. So when I connect the dots here, I'm going to, or when I connect to this y-intercept, it's going to be something that looks like this, all y or negative y values. And hopefully it should make sense that I never actually come up anywhere in this section, because as long as I'm subtracting 4 from whatever value I put in here, there's no way I can get a number for y that's in between 0 and negative 2. So this is kind of like the ceiling for my function in this section. And then applying the same logic as I did over on the other side, if I have an x value that's greater than 2, this fraction will always be positive, so my final section looks something like this. Now, if you can't reason through when these y values are positive, when they're negative, just think about, you can always put in a value. I can always plug in 3, do the workings out, and then figure out where that graph is. So why don't you try this example, kind of similar. I've got two vertical asymptotes. Pause the video, give this one a shot, and see how it goes. All right, and here is my solution for the U-try number 6. In our final example here, we want to graph something that looks like this. This one's a little bit more complex than the last, or at least a little bit different, maybe not necessarily more complex. Let's go through the same motions we have been so far. For the vertical asymptote, I want to set denominator equal to 0. So let's do that. I'll set x plus 1 equal to 0. That means that x equals -1 will be one of my vertical, or my only, in this case, vertical asymptote. So let's plot that. All right, and then over here, let's take a look at the y-intercept. I'll set the x equal to 0. So I have y equals 2 times 0 minus 2 over 0 plus 1. So really these guys cancel and they go away, and I have y equals -2 over 1, or y equals just -2. So I'll have a y-intercept of 0, -2. Next up, let's take a look at the x-intercept. In this case, I do have a numerator with an x in it, so that means that I can really set the numerator equal to 0, and I can solve for x. So 2x minus 2 equals 0, and if I solve for x, I get x equals 1. So I do have an x-intercept here. Oh, let's go blue. I do have an x-intercept here at x equals 1. Okay, now let's talk about end behaviors. So the limit as x goes towards infinity. This is where it gets a little bit interesting here. If I were to plug in really, really large numbers, what's going to happen here is I kind of have to think about the effect of each of these terms. Let's take a look at just the numerator for a second. If I'm plugging in a really large number, then my numerator is kind of doubling in size. This -2, as I plug in bigger and bigger numbers, this -2 doesn't really affect the numerator as much as it does when I'm talking about smaller x values. So if I put in like 1, for example, 2 minus 2 has a very large effect. It's reducing it by really 100%. But if I put in 1,000,000 and I double 1,000,000 and then I subtract 2, this 2 kind of has less and less of an effect on my numerator. So basically I'm doubling whatever my x value is in my numerator. In my denominator, a very similar thing is happening here, where this 1 becomes less and less important as I put in larger and larger and larger numbers. And so what I'm interested in when I'm thinking about where this graph approaches as x goes towards infinity is the ratio between the coefficients of these x values. I'm doubling my large x values on top, and I'm just keeping my x values the same on bottom. So I'm going to have a 2-to-1 ratio between those things, which means that my y values are going to approach, since there's a 2-to-1 ratio, they're going to approach 2. So that's going to be the same if I'm going to positive infinity or negative infinity. My limit in both cases, as I approach positive or negative infinity, is going to be 2. And I want you to pause the video if that makes you a little confused and think about what that means, especially when it comes to kind of identifying the ratio between these very large numbers. And when in doubt, plug in numbers. Plug in really large numbers, plug in really small numbers, or really large negative numbers, really large positive numbers, and see if you can see where this thing is trending towards. That means I'll have a horizontal asymptote of y equals 2. So let's graph that. Y equals 2. All right, and now I'm ready to start to put some graphs on here, and I'll do just what I did before. I've got these 2 points that kind of anchor my graph here. That looks something like this, and my other section will be kind of in the opposite quadrant, so it looks something like that. And when in doubt, you can plug in some points or plug in some x values and see what comes out. Final try here. I've got once again I have a fraction, a rational function, a numerator, and a denominator. Pause this video, give it a shot, and see if you can't figure it out. And here are my solutions for this problem here. You can always play around with these graphs using Desmos or your graphing calculator, change the numbers a little bit, see how it affects with a graph, and hopefully this made some sense.